All right. Hello, IB Physics. Um, Welcome back from spring break. Sorry for the delay. I was trying to get you guys a better internet connection and I failed. And I was getting frustrated and it took longer than I thought it was going to take. Hey, Jackson. So I'm here drinking some Squirt. I find Squirt to be very refreshing. I don't know about you guys. Probably the most refreshing soda for me. So if you were supposed to have been testing this year, then you're not going to test this year. In that case, your grade, your IB grade, which you would receive this year, is based purely on the predicted grade that I give you and the IA. So if you are testing, we're going to test this year. I absolutely need your IA because I need to use that. So I think there's only one student who I need their IA and who was testing this year, and that's Christian. So if you know Christian, talk to him, say, Christian, turn in your IA. Gosh darn it. Hey, Sofa. Hey, Ben. Hey, Michael. Hey, Spicy Pepper. Hey, Michael, I haven't heard from you in a while. Good to hear from you. All right. So we're going to start talking about climate change today. Before spring break, we were talking about energy production. Now we're going to talk about climate change. So one of the things I want to do IAs still get graded if you're not testing this year? Yes. Akshay, they will be graded. I still need them. But the difference is just that I'm not prioritizing those at this time. So I need to grade all the students' IAs who are testing this year before Friday. So I've graded about half of them already. Let's see, I've graded Charlie's, I've graded Galen's, I've graded Victoria Catano's, I've graded Asia's, I've graded Sophia's, I've graded Aiden P's. So yeah, I've graded about half of the ones for this year. All right, so here's a cool graph. This is a graph of brightness versus wavelength. Okay. So like, let's say you're looking at a light bulb or something. A light bulb is going to have a brightness versus wavelength graph. And maybe it looks like this. Okay. If the brightness versus wavelength graph looked like that, then that would mean that all of the brightness of the light bulb is concentrated at this wavelength. So maybe that wavelength corresponds to blue, in which case that would be a blue light bulb. If a light bulb had a brightness versus wavelength graph that looked like this and had its spike over here, then that would mean most of its light is coming out at this wavelength, which would maybe corresponds to red or something. Okay. You could even have, so let me draw a couple of brightness versus wavelength. Brightness versus wavelength graphs. Maybe it looks like this. This would be kind of cool. So this brightness versus wavelength graph is emitting most of its light at this wavelength and a little bit of light at this wavelength. Okay, so maybe if this corresponds to blue and that corresponds to red, that it's emitting a lot of blue light and a little bit of red light. So, maybe it looks like purple or something. I don't know. Or not purple, but just a combination of the two. What would white light look like? Has anyone ever heard that white light is all of the colors mixed together? So a light bulb that's emitting white light has a brightness versus wavelength that looks like this. It's just a flat graph because you've got all of the colors equally. Okay. Why is it that I've drawn blue to the left of red on this graph? Well, that is because blue light has a shorter wavelength than red light. Okay. The squirt is so refreshing. Okay. So let's suppose we were to look at, so there's this thing, and it is called a black body. And a black body is basically an object that absorbs all light that hits it. So there's no reflection from a black body. It just, everything that comes in gets absorbed. That's why it's called a black body. Okay. Now, as it's absorbing the light, it's heating up because light carries energy. Okay. So I sort of ironically, black bodies, if you were to look at a black body, it is not necessarily black. And the reason is this: it's at a certain temperature. Akshay is asking an important question of what does squirt taste like. It is a grapefruit soda. So it kind of tastes like a little bit like 7-Up, but with a more of a grapefruity taste to it. You should check it out sometime. All right. So a black body is not necessarily black. Not necessarily black. And so why is it not necessarily black? Because things that have a non-zero temperature emit light. Okay. So it's not necessarily black because the temperature of the thing is not equal to 0. Okay. Anything that has a temperature that's not absolute 0 is actually emitting a little bit of light. Did you know that you are emitting light right now because you're not at a non-zero temperature? Okay. Why don't you glow in the dark? Well, actually, you do glow in the dark. It's just the wavelength of light that you are giving off is not a wavelength that human beings can see with their eyes. But if you had the right camera, you could actually see someone glowing in the dark. And that's how night vision cameras work. Okay. So basically, it's not necessarily black because temperature equals 0. So why is it called a black body? It's because it doesn't reflect light. That doesn't mean it can't produce its own light. Do you understand the difference between reflection of light and producing light yourself? Okay. So a black body can produce its own light because it has a non-zero temperature, but it cannot reflect light from the outside. Anything that comes from the outside gets absorbed by the black body. Okay. So if we were to do one of these wavelength versus brightness graphs for a black body. What does it look like? Well, it kind of looks like a bell curve. It kind of looks like an asymmetric bell curve, like that. Okay. The reason that it's a little bit asymmetric is because you can't have a wavelength less than 0. So, okay. So what we can see is that there's a wavelength where the brightness is at a maximum. Okay. So this is basically what we perceive as the color of the object. Now, let's suppose that this is a medium temperature black body. So it's emitting light like that. How do you think this graph would change if it was at a hot temperature? Well, have you ever noticed that when you turn on the stove and the burners get going, they turn red, right? The burners turn red. Do you know what the hottest color of flame is? Maybe you've heard that the hottest color of flame is blue. Okay. So actually, the hotter something gets, a black body gets, the bluer its color will be. So if we were to draw the same graph for a hot temperature, its peak is going to be at a bluer wavelength, which is a shorter wavelength. Okay. And furthermore, its peak will be taller. Okay. So its peak is going to be taller, and the wavelength is going to be shorter if it's hotter. What if it is a colder black body? If it's a cold temperature, then that means it's going to be redder. Okay, so its peak might be over here at big wavelengths. And furthermore, the peak is going to be smaller. So it might look just like this. Okay. So in general, the hotter a black body is, the bluer it is, and the more light it emits. Okay, so the hotter the black body gets, the bluer, so that basically the peak of this graph shifts to the left the hotter it gets, and it gets taller and taller and taller. Okay. It's possible for a black body to be so hot that the wavelength is so short that human beings can't even see it. I just got a call from Mrs. C. She can wait. You guys take priority. Actually, I'm almost done with my lesson here. So there's an equation. It's called the Weins Displacement Law. Okay. And what it says is it tells you the wavelength where the peak occurs. So if we look at this graph, these graphs, this is the wavelength where the peak occurs. This is the wavelength where the peak occurs. What is the wavelength at which most of the light is being emitted? Okay. So Weins displacement law tells us what is the location of this peak. It doesn't tell us how tall it is, but it tells us what wavelength it occurs at. And the wavelength at which the peak occurs is, okay, 2.9 times 10 to the minus 3 meters times Kelvin over the temperature. So what you can see, so this is the temperature of the black body, and this is the wavelength that it's emitting most of its light at. Okay, so you can see that as the temperature increases, the wavelength of the peak decreases, which means that it gets bluer. So it's the exact same thing that I said on the previous page. As the temperature goes up, the wavelength goes down. Okay, so this is actually really cool. So we could actually take this equation and we could reverse it. We could say temperature equals 2.9 times 10 to the minus 3 meters Kelvin over the wavelength of the peak. Okay, and we can actually use this as a thermometer. Okay, how do we know what the temperature of the sun is? Have you ever thought about how do we know what the temperature of the sun is? Do we have like a thermometer on an extra long stick and we extend it into the sun to measure its temperature? No, we don't have that. So how do we know what the temperature of the sun is? What we do is we take a picture of the sun and we look at the light that's coming off of the sun and we look at what is the wavelength where most of the light is coming off at. And it turns out that for the sun, the wavelength is mostly yellow. Okay. And we plug it into this equation and we can get the temperature of the sun. And we get that it's about 5,000 Kelvin. Okay. So I think that's kind of neat. You can tell the temperature of objects that are really far away by taking a picture of it and seeing where is the peak wavelength. Okay. So I like that a lot. This equation only works for black bodies. But it turns out that many, many objects behave like black bodies. The sun behaves like a black body because the sun doesn't reflect light, really. The earth actually behaves somewhat like a black body. So all these things actually behave a lot like black bodies. So we can predict their temperature from the wavelength of the light that's coming off of them. So we're going to delve into this deeper tomorrow. And I hope you guys have a good rest of the day. Bye now.